Thank you for the invitation. It's a pleasure to speak here. Today I'll introduce a log minimal model program for mgbar. I'll begin with some generalities about mgbar. Then I'll explain what the program is about, and then finally I will survey the current progress of the program. So let's start with some definitions. Mg will be the moduli space of smooth curves, smooth genus G curves. It's a quasi-projective variety. Which is irreducible and has dimension 3g minus 3. The singularities of this variety are very mild. As a stack, Mg is a smooth. So this is a smooth DM stack, Deligne-Mumford stack. And as a result, as a variety, Mg has only finite quotient singularities. In fact, they can be seen to be terminal. So pretty mild terminal finite quotient singularities. And this follows from rate tie criterion. So most of this was known classically, at least around say 1960s. The kind of result that we know about Mg and which requires something that besides just having this moduli space Mg is the following. Mg is of general type for large G. And this is due to Harris-Mumford from 82. They did the case of odd genus, and then Eisenbach and Harris completed the proof for the remaining genera. Now this is more recent result, and what it says is that Mg is very much not unirational when genus is large. Namely, the general curve of genus G cannot be written down in terms of a system of 3g minus 3 free parameters. However, the result, the theorem, requires having a compactification of the variety Mg. So we need to compactify, and to compactify I need to introduce a definition. A curve C is Deligne-Mumford stable if the following conditions hold. If, first of all, C will be reduced and C has at worst nodal singularities. These are curve singularities which locally analytically look like this, and the relative dualizing sheaf, which in this case exists, of C is ample. Right, so here's a picture of a stable curve. We can have nodal singularities, and stability is a condition number 2. What it says is that if you have a rational component, a smooth rational component, it has to meet the rest of the curve in at least 3 points. And so we can consider the moduli stack of such things. So the Mg bar moduli stack of DM stable curves. And clearly this will be a compactification, or this certainly is an enlargement of Mg. And in fact, it's a compactification, namely mg bar has course, so mg bar has projective course moduli space which gives us a compactification of mg. And we understand very well how this compactification works, namely the complement of the interior, the so-called boundary delta, which splits into the union of irreducible divisors. So these are irreducible divisors, and these divisors parameterize stable curves of the following forms. Delta naught parameterizes curves with the node which looks like this, so-called non-separating node, meaning that when you normalize at the node, the normalization is still irreducible. And delta I parameterizes curves, stable curves, which are generically union of two smooth curves of genera I and G minus I. All right. Now to explain how the Harris-Mumford result uses a compactification, let me describe first the Picard group of mg bar. We already have with irreducible divisors delta I. mg bar, just like mg, has finite quotient singularities, so every divisor is a Q-Cartier. There is an extra divisor class which doesn't come from boundary, and to describe it, let's consider the universal family over mg bar. The Hodge bundle E is a push forward of the relative dualizing sheaf of this universal family, namely the fiber of the Hodge bundle at a stable curve C is just the space of global sections of the dualizing sheaf of C. And lambda, the Hodge class, is the first term class of the Hodge bundle. And the theorem of Harrer says that lambda generates a Picard group of mg, and so the Picard group of mg bar as a stack is a free group generated by lambda and delta i's. All right. And well, in fact, we can compute the canonical class of mg bar in terms of lambda, in terms of the generators of the Picard group, and it turns out to be 13 lambda minus 2 delta, where delta is just the sum of the boundary divisors. Right. And so the way the Harris-Mumford theorem is proven is by showing that the canonical divisor is represented by an effective divisor. It's effective, in fact, it's big, and the statement about general typeness follows from that, and also from the analysis of the singularities of mg bar. So let me, before I get to the questions about effective divisors, let me start by stating some questions about mg bar which are still open. So we know a lot about mg bar, but we also don't know a lot. So open question number 1 is to describe, as a problem, describe the ample cone, or the NAF cone, of mg bar. So we don't know what that is. There is a conjecture called the F conjecture. I don't want to go into it right now, but I want to say a few things that we do know about this problem. we know ampleness or naffness of some divisor classes. Let's start with, well, it's known that lambda is naff. So lambda is naff. And in fact, if one considers a regular map from MG bar to the Satake compactification of the moduli space of principally polarized abelian varieties of dimension G, this map sends a curve, a stable curve C to the Jacobian of the normalization of C. So if the normalization is reducible, it's just a product of the Jacobians of the irreducible components of the normalization, and that usually such a product is precisely sits in the compactification of in the boundary of this compactification of AG. So this map is given by lambda. So lambda is a pullback of some natural ample line bundle, of the natural ample line bundle on the AG Satake. So it's naff, in fact semi-ample. There is a theorem of Kornalba and Harris which says that, at least if you look at the line bundles of the form S lambda minus delta, this line bundle is ample if S is at least 11. Right, so in particular, 11 lambda minus delta is precisely naff, and is 0 on the following families, precisely on families B, where the family of stable curves is as follows. We have a constant family of genus G minus 1 curves, B cross G minus 1 curve, and to such a family we attach a family of genus 1 curves, and we let the genus 1 curve vary in moduli. So we vary the J invariant of the elliptic curve. So this is a family of so-called elliptic tails. Right. So, so this divisor class 11 lambda minus delta can be rewritten from this formula as follows. Right. And now, this divisor is naff by Kornalba-Harris theorem. It can be shown that it's big, and Kawamata base point freeness theorem tells us that this divisor is actually base point free. So this is base point free, and as a result we obtain a morphism given by this divisor. The target of this morphism I'll call 9/11, MG 9/11, and by definition this is simply the product of the following graded ring. Right. So we know that this morphism exists by by base point freeness of the line bundle, and the natural question is to ask, well, what is this target? I mean, the target is given as a product of some graded ring, but is there a different description of the target? And in fact there is. And so to give the description of the target of this morphism, let me give another definition. A curve C is pseudo-stable if well, it's reduced and C has at worst hospital singularities. These are curve singularities which are locally analytically look like this. And as before, omega C is ample. Right, so it's omega C is ample, and an extra condition that we need to for pseudo-stability is that C has no elliptic tails. All right, so its elliptic tail is a curve. Curves with elliptic tails are stable curves in delta 1. Right, so these are not pseudo-stable. And now turns out that the target of the morphism given by k plus 9/11 delta has a modular interpretation. So it's precisely the moduli space of pseudo-stable curves. And this is the theorem this was discovered by Brandon Hassett and David Hume in 2006. So they prove that Mg of 9/11 is a moduli space of pseudo-stable curves. I should say that the pseudo-stable curves were introduced quite a bit before this theorem. I mean, they were discovered by a student of David Giesecke, David Schubert, in his thesis. All right. Okay, so now we're at the point where we've reached the boundary of the Neff cone by right, when we look at the divisor in 11 lambda minus delta, it's on the boundary of the Neff cone. And in fact, so I want to leave the realm of Neff divisors, and I want to discuss effective divisors on MG bar. So open problem number 2, wide open, is to describe the effective cone of MG bar. And well, surprisingly, not only we don't know this, we don't even know precisely how the effective cone of MG bar looks in the cross section given by the line bundles of the form A lambda minus B delta. So here A and B are positive. Right, so we know if we replace effective by ample, we know precisely what the ample cone intersect with this two-dimensional cone is. The answer is given by the Cornell-by-Harris theorem. But we don't know the answer in the effective case.
Do we know until it's
24? We know in some genera. I don't think it's 24. It's less. Maybe about 12 or 13. Like low teens. Yeah. I mean, genus 10 certainly. Genus 11. So, all right. Now, why would we? Let me now observe also that span of lambda and delta. All right. So it's a two-dimensional cone spanned by lambda is delta is the same thing as a span of canonical divisor and delta, and we can go from one to the other by a simple formula, namely S lambda minus delta is 13 over S over 13 of K mg bar plus 2 minus 13 over S delta. Right. All right. Now, although we don't know the precise description of this intersection, we do know something, and namely, if I look at this two-dimensional cone spanned by lambda negative delta, I will be interested in the effective part. So let this be an effective cone. And right, I'm going to be looking at the slope. So divisor D here is represented by so there is a slope as effective, which gives us the boundary of the effective cone. I mean, it's positive because negative delta is certainly not effective. And we've seen that 11 lambda minus delta, this part is ample. And now, from the log minimal model program, and in particular from finite generation of log canonical rings by Birkar, Cassini, Haken, and McKernan, we know that this part of the effective cone is divided into chambers, where each chamber corresponds to a birational model of mg bar. And so we have a subdivision of the effective cone into chambers. Turns out that the chamber, which is adjacent to the ample cone, has boundaries given by slopes 11 and 10. And then the next chamber has boundary given by the slope 39 over 4. But we don't know, I mean, this is the extent of our knowledge. We don't know how many chambers there are. And in particular, a $100 question is, what is, well, basically, is S effective less than 6, right? And if you answer this, Ian Morrison is a guy to claim your money, right? Or Gabi Farkas, I guess. It depends on which way you solve it. So we don't know what S effective is, but let me just say that Harris, Mumford, Eisenbahn showed that when G plus 1 is composite, then there is a so-called Brill-Noether divisor on mg bar, and it's effective, and its effectivity implies that as this boundary of the effective the slope of the effective cone is at least 6 plus 12 over G plus 1, right? And in particular, this is less than 6 1/2 for G greater or equal than 24. And this is precisely the range. So in this case, 6 1/2 is precisely the slope of the canonical divisor. So in this case, the canonical divisor lies in the interior of the effective cone, which gives the proof of the fact that the mg bar is of general type. Now Farkas improved this bounds, and he shows that in fact S effective is less or equal than 6 plus 10 over G. However, again, this is asymptotically, this is 6. No one has exhibited an effective divisor of slope greater than 6. Smaller than 6, I'm sorry. And he shows that, again, Farkas in 08, in 10, around 2010 shows that M22 bar, using his improvements, he shows that M22 bar is of general type as well. Okay. Now we're interested in this decomposition of the effective cone, at least in this cross section of the effective cone. And for each divisor in the effective cone, we can look at the associated birational model. Namely, if I can make the following definition. Mg of alpha will be proj of the graded ring of sections of the log canonical divisor k plus alpha delta. And here alpha is a rational number in the interval from 0 to 1. And again, the observation is k plus alpha delta can always be written as approximately as proportional, so numeric proportionality to 13 over 2 minus alpha lambda minus delta. Right, so the divisors of the form k plus alpha delta are precisely the divisors in this part of the effective cone. And what the log minimal model program for MG bar attempts to do is to give descriptions of these log canonical models. In particular, we've already seen that MG bar of 9/11 is a moduli space of pseudo-stable curves, and it turns out that there are two more models that have the nice modular description. So I need to make another definition, an alternative stability condition for curves. A curve C is C-stable, or respectively H-stable. I think the proper name is semi-stable, but I'll abbreviate. If, well, first we have a condition on singularities. C has at worst tach nodes. These are curve singularities locally analytically isomorphic to this. So two branches which are tangent, smooth branches which are tangent. C has no elliptic tails, as in the case of pseudo-stable curves. This is a C-stable case. The H-stable case says C has no, respectively, no elliptic tails, no elliptic bridges. These are curves with elliptic bridges look like this, and also no elliptic chains. I won't go into detail what elliptic chains are. That won't be important. And I mean, as always, we like our curves to be canonically polarized, so omega C is ample. And so the result which gave impetus to the log minimal model program is the following theorem of Hassett and Hune. So now the preprint was from 2008, but the paper is going to appear in Annals, I guess, at some point, and 2013, I guess, this year. And it says that MG bar of 7/10 is a moduli space C-stable curves, and mg bar of 7/10 minus epsilon is a moduli space of H-stable curves. So here epsilon is some small rational number. And okay, so these are still compactifications of Mg, and these are new compactifications of Mg. I should describe how the rational maps between these different compactifications of Mg look like. And so we have now 4 different compactifications, and in every genus they fit in the following diagram. We have mg bar, the Deligne-Mumford compactification. This maps to mg of 9/11. And this map is a divisorial contraction and contracts the divisor, boundary divisor delta 1. Then we have a map from this one to mg of 7/10, and mg of 7/10 minus epsilon maps here as well. The resulting rational map is a flip, and what this flip does, it flips curves with elliptic bridges to curves with stack nodes. Right, namely, if you have a curve with elliptic bridge, you forget the datum of elliptic bridge, and you map this curve to a curve with a tack node by identifying the tangent spaces as 2 points of attachment of the elliptic bridge. That requires a choice of the isomorphism between 2 vector spaces of dimension 1, so the map is not regular, it's just a rational map. So this is a tack node. All right, so this is true in every genus greater or equals than 3. Right, and as far as results in arbitrary genus go, this is really all we know about the log-Monell model program. Right. Now I want to describe in low genus, we know quite a bit more, and so I want to survey what is known in low genus. I'll start with well, the baby case, which is genus 2, and so this is due to Brandon Hassett. We don't have the whole picture. We don't have this picture in genus 2. We just have the first contraction. So we still have a space M2 bar of 9/11. This is a moduli space of genus 2 curves with adverse cusps. And well, since a genus 2 curve is a hyperelliptic curve, we can think of a genus 2 curve as a double cover, generically of a P1, branched over 6 points. And what Brandon shows is that this space can be described as a GAT quotient of the space of degree 6 homogeneous, degree 6 binary forms by the action of PGL2. Right, so we take a polynomial of degree 6 and gives us a genus 2 curve. The strictly semi-stable points in this GAT quotients are with strictly semi-stable points with closed orbits there is exactly one such, And this is the binary form where you have two zeros, so multiplicity is 3, and the resulting double cover is a bicuspidal curve. All right, so y squared equals x cubed. And the whole boundary divisor delta 1 gets contracted to this single point, to a point given by this bicuspidal double cover. Okay. Now I should, as a matter of notation, it will be useful because in the remaining genera to use the following notation. I'm going to write mg of AB to denote mg of alpha denotes mg of alpha in the case mg of alpha is constant for alpha in this interval. So A to B will be an interval, and I will write mg of AB to denote mg of alpha for any alpha in this interval. Right. So again, we know that there are finitely many. For every genus, there are finitely many intervals which subdivide the this two-dimensional cross-section of the effective cone, and for each interval we get a model, a birational model of mg bar. So let me describe what happens in genus 3. This is the work of, again, David Hune and Yongnam Lee from 2010. We have, as before, we have the picture with the first contraction and the first flip. Right, I will now use my new notation. This is mg of 9/11 to mg of 7/10. There is a flip to m3 of 7/10. And they show that the second interval is, I believe, 17/28. Right, so there is this m3 bar of 7/10. And there is just one more step in the program where we have a log canonical model m3 of 17/28. Strictly speaking, this is closed. This part of the interval is closed, and this is 5/9. And what this last model is, log canonical model is, well, they discovered that this is a GAT quotient of the quartic plane curves. So a quartic plane curve is a genus 3 curve, and if we look at the GAT quotient of this quartics, we recover this last log canonical model of M3. So this is the GAT quotient PGL3. And well, for the future, let me just note that a space of quartics is precisely the Hilbert scheme of canonical genus 3 curves. Right. So in the case of genus 3, the Hilbert scheme of canonical curves is just a projective space, and its GAT quotient gives us the final log canonical model. Genus 4. In genus 4, we have again the first two steps are as in every genus, and what Hyun and Lee show is that let's see, we have mg of 7/10 minus epsilon is constant on the interval from 7/10 to 2/3, and there is a regular map from this space of genus 4 H stable curves to M4 of 2/3, and this contracts certain curves which look as follows. We have two components meeting in a node, and a point P is a Weierstrass point on one of the components. Right, so not only we have a map between log canonical models, this log canonical model has a modular interpretation. Unfortunately, at this point, we don't know what happens next. We don't know what the interval, what interval comes up to 2/3. But there is an observation about canonical curves of genus 4, which allows us to see what the program looks like at the very end. So a canonical curve of genus 4 is well known to be a 2-3 complete intersection so this was Youngman's work with David Hyun, and we have a 2-3 complete intersection in P3, which is a canonical curve generically, and we can look at the projective space parametrizing all quadrics first in P3, and this is just a P9, and on P9 we can look at the vector bundle. So let E be the vector bundle such that the fiber of this vector bundle at a quadric Q is precisely this vector space of all cubics restricted to the quadric, right? So E, rank of E is is 15, 16. 16. Now, projectivization of this vector bundle parametrizes rises to 3 complete intersections in P3. But now, of course, two 3 complete intersections define the same curve if they lie in the same orbit of the PGL4 action. And so it's a natural question to look at the PGL4 quotients of this projective bundle. Okay, now to give you the answer, let me just observe that the Picard group of PE is generated by 2 classes, class H and class eta, where H is just a relative of 1, and eta is the, well, I guess eta is a let me just do this. Eta is a relative of 1, and H is the, I'll abuse the notation slightly. I'll write it as this. It's a pullback of O of 1 from the base of the projective bundle. Pullback, where pi is projection. Right, so we have two classes, and to have a quotient, a GAT quotient by PGL4, we need a linearization, which is a line bundle on which PGL4 acts, and we have here a choice of linearizations. Right, so we can let L of t to be t eta plus h. Right, so at t equals 0, we just get a pullback from of O of 1 from downstairs. And now the theorem, which is due to Castellano, Martin, Jensen, and Laza, and this is from last year, says that the GAT quotients of this projective bundle of P of E with respect to this varying linearization are log canonical models of M4 bar for values of alpha in the range from 5/9 to 8/17. Well, I could have put in 0 here, but the log canonical model at 8/17 is empty. So we don't care about those values. And so this corresponds to values of t between 2/3 and 0. Right. So not only they construct the log canonical models in this range as GAT quotients, they obtain the modular interpretation. So they describe GAT quotients that precisely the semi-stable points occurring in each GAT quotient. So to sort of give an idea of complexity of the description, let me just tell you how many quotients there are. And so this is quite interesting picture. Namely, we have, this is part of the theorem, we have the following intervals. From 5/9 we have an interval up to 23/44, and then we have an interval from 23/44 to 1/2, and then we have an interval from 1/2 to 29/60. Now there is a map here to M4 from 29/60 to 8/17. This is a final log canonical model. Here we have M4 1/2. So now again, this is a flip from here to here. This is a flip, and they have a very precise description of what this flip does. I'll say it in a minute. M4 bar of 23/44. Now, just to give an idea, right, and this is M4 of 5/9. Right, so to give you some idea, the last flip in this picture takes a curve with which looks like an intersection of a singular quadric with a cubic which passes through the vertex of the quadric, and it replaces such a curve in this space by a union of a double conic with a smooth conic on a smooth quadric. This is the description is quite involved. The last map contracts. This is a regular map. It's a divisorial contraction, and it contracts the Petri divisor, the divisor of curves lying on singular quadrics, to a single point in this last canonical model, and this single point parameterizes triple conics. Now, at this end of the picture, the model corresponding to alpha equals 5/9 turns out to be a GAT quotient of the Chow variety of canonical genus 4 curves. And this is work of, this is their earlier paper from 2011 when they describe this model very precisely. So I should say that there is a different GAT quotient which occurs in genus 4. It's slightly namely, I've described this last log canonical model in a slightly different terms. The final log canonical model can be described as a GAT quotient of the 3 curves in P1 cross P1, a smooth quadric, by the automorphism group of P1 cross P1. Okay. And in particular, it follows from the description again that the Petri divisor is contracted by this rational map. Contracts delta 1, delta 2, Petri divisor, and we can give precise definitions of what loci are flipped. And for example, this map flips the hyperelliptic locus. And other some other geometrically defined loci in M4 bar. Okay. So I should say that so in genus 4, let me reiterate that there is an interval of alpha values for which we don't know how the log canonical models look like, but it is in Castellano, Martin, Laws, Jensen's, and Laws of papers, they conjecture that or speculate that there are just 2 threshold values which break this interval into 3 intervals. So there are 3 more log canonical models which are not yet constructed. So let me move on and describe what we know in genus 5. This will be the last genus that I will discuss. In genus 5, we know even less, which is natural. Besides the models of Hassett and Hune, there is just one model, log canonical model, that's been described explicitly, and it again comes from canonical genus 5 curves. If we consider a canonical genus 5 curve, it's a 2-2-2 complete intersection. As long as it's not hyperelliptic or trigonal, and the parameter space of 2-2-2 complete intersections is a Grassmannian of nets of quadrics in P4, and together with David Smythe, we've looked at this Grassmannian, and we've analyzed the GAT quotient of this Grassmannian with respect to PGL5. So this is our recent paper in which we analyze the Grassmannian of nets of quadrics in P4, and in particular we study its GAT quotient by SL5, and we show that this GAT quotient gives us a log canonical model of M5. This is a final non-trivial log canonical model, and it corresponds to the interval of alpha from this number to 3/8. And we describe the geometry of the resulting rational map. Namely, we show that the rational map F from M5 bar to this last log canonical model contracts all the boundary divisors, and it contracts the trigonal divisor to a point. Right, and in particular, this gives another proof that the trigonal divisor, this is a Brill-Noether divisor in genus 5, has the lowest possible slope. So it's sort of, this implies that this was the statement about S effective for genus 5 was known before, but I mean this, the fact that trigonal divisor is contracted also implies that S effective is 8. So the boundary of the effective cone is given by 8 lambda minus delta. And a curious observation that we deduce from the GAT analysis is that the pullback of O of 1 is given by the following divisor, which one may recognize as a divisor of vanishing theta nulls on M5 bar. Ah, 0. Thank you. So that's a divisor whose class has been computed by Taxidori Bigas. Well, this is the extent of our knowledge about the log minimum model program. I mean, there is, I should say that there is a work in progress in which we're describing the second flip together with Jared Alper and David Smythe, the second flip of MG bar in every genus. But as you know, as to what has appeared in print, I've showed you everything that we currently know. So I'd like to stop here. Thank you very much.